Hey everybody, this is Larry. This is day 9th of the July Leetcode Daily Challenge. Happy Friday everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Longest increasing subsequence. Yeah, I usually start these live, so if it's a bit slow, fast forward or whatever you need to do. This one is a tricky one. So there's you can really do a long video on this one, especially with the n log n one. And it's kind of funny because way back when I was first starting on competitive or just doing these things in general, a lot of libraries didn't even have hash tables really, or they were not fast enough to be really used. So the n log n one was actually kind of tricky to implement for a long time, so that people knew about it, but it wasn't a requirement, or like it doesn't come up in a problem until I guess maybe more recently. And by more recently I mean about the last 10 years, where maps and hash tables and stuff like that are more prevalent, and you're actually expected to use it in a library and stuff like that, because way back when that wasn't the case. Okay, so what is n here? N is 2500, which is probably already a little bit slower on the n square type. This is kind of a really tricky one to do n log n on, because I think it doesn't really this is not really a progression, the n square one is a dynamic programming problem, and actually probably one of the earlier dynamic programming problems that you're asked to learn and solve. And it's and I really like that one because with that one is very easy to visualize with respect to it being the longest path in the DAG, and from that you get to kind of really understand that dynamic programming operates on the DAG, and from that, like you kind of play around with the graph aspects of a dynamic programming solution. That being said, let's try to do the n log n one. I'm not going to go over the n square one, even though I guess it's like two lines of code. So basically the idea is that, okay, you have something like this, where let's say I guess just one, there's at least one item. Why is this red? Did I mistype something? So if A is greater than, I don't know if this is strictly increasing or strictly increasing. Okay, fine. So that's basically it, right? Yeah, so this is going to be the n square solution, and this solution is basically going over, okay, for every number we look at a previous number to see where like if you think about it recursively, for every index you ask, okay, if this is the last number in a subsequence, what is the longest subsequence that ends with this number, right? And the longest subsequence that ends with this number is if it adds this number to a previous number that is smaller, right? So then that's basically the idea here is, okay, if I is bigger than j, then we add num sub I to the sequence that's num sub j, and the sequence that ends at num sub j is dp sub j, and you add 1 to it because you're adding the current item, and you just kind of max over it. So this is going to be probably right, unless I have some weird typos, right? And of course this is going to be n squared, because because you have two for loops, one going from one going to n and one going to j, right? Oh, sorry. Yeah, this for loop is n, and this one is also going to be n roughly because it's n choose. It goes from, you know, because here it goes 1 plus 2 plus 3 plus 4 dot 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 plus n, which is equal to n squared roughly, or O of n squared anyway. I know it's n times n plus 1 over 2, but yeah, so this is going to be n squared. So the question is, okay, how do you do the n log n1? Right, and n log n1 is actually kind of tricky, and definitely if you're still struggling with dynamic programming and stuff like that, I recommend learning the dynamic programming part first, doing it bottoms up, top down. There are actually a couple of ways to write this as well for space optimization, because the way that I write it doesn't, but yeah. So then the other question is, okay, so how do you do the n log n1? N log n1 it actually requires a sort of observation that is a little bit tricky. And the observation on n log n1 is that, okay, it kind of reminds me a little bit of the binary search problems of, okay, for binary search, what is the for binary search, you're trying to binary search the answer, right? And this is kind of similar to that idea with DP. I think, okay, let me think about another way to explain it. Okay, so now that we have the DP, what are we doing here, right? Let's go over there. Maybe this is slightly easier to go over. So, and sorry about that. I am explaining these live from my head, so maybe the flow isn't that great because I am trying to think about how to explain it as well. But the idea is that, okay, if we look at this thing, all we're trying to do is, okay, like if we try to write it another way, another way that we may write it is, okay, right, is that, okay, I say okay last, sorry. Give me all j's that are smaller than me, and give me the max or the longest subsequence, right? And here there is a sort of a weird observation to make here, which, to be honest, I don't know if I would have gotten it easily, but you basically do it on the answer, right? So the idea is that, okay, let's say I have a subsequence of length 1, right? And this is actually greedy as well. Does it have negative numbers? It does, okay. So this is longest subsequence of length 0. So now we kind of ask a similar but not quite problem as we kind of go through this array, right? Because basically we're kind of reversing the problem on its head. And here, now we go through the numbers one by one still. Zero with the last number being subsequence of 0, right? So here we go, okay, let's say we have this number num sub I, and we want to add it to, so we ask our question of, hey, can we add this to a subsequence of length 0, right? So let's do it for loop another way. Length of subsequence. Let's call this DP as well, actually. dubious though, but yeah. So let's set this dp, and then we go if num sub I is less than dp sub j, then what does that mean? That means that in a greedy kind of way, in English, what you're asking is, okay, so right now we can make a longer subsequence of length j with dp sub j number, right? So that's the number, that's the last element on a subsequence of that length. But if it's smaller, then that means that if you think about it, let's say we have some sequence like, I don't know, 1, 2, 3, 4, 20, right? And now num sub I is equal to 10. Well, if we're doing it in a greedy way, we can always replace the 20 with a 10 because 10 is smaller. And in theory, it would always be a move that allows us to squeeze more number in later on. So that's basically kind of the idea behind it. So here, in that case, then dp sub j is equal to num sub I, right? And then at the very end, so that's basically the idea. And then at the very end, if dp sub the last element is less than num sub I, strictly less than, we can add a new number, right? And the English way of saying this here, because I like to explain this in English, is that okay, so, and you could actually technically do this with all the other numbers, but it's just that it doesn't change anything, or that's effectively what you're doing anyway by doing this thing. But basically this is saying, okay, give me the longest sequence you have. If the longest subsequence that you have, the last number is smaller than the current number, then we add this number to, then we create a new longest subsequence by adding this number to it. So for example, let's say you have a sequence of 1, 2, 3, 4, 5 again, and your num sub I is equal to 10. Well, we know that there's a subsequence of length 5, so now we can create a subsequence of length 6 by adding 10. So that's basically the idea here. And here, the answer, of course, is going to be just the length of dp, -1, I think, maybe. Yeah. Right. And that will get you the answer as well. Okay, right? Of course, the first thing that you might notice here with this dynamic programming is that let's actually change this to I, and but yeah, the thing to notice about this dynamic programming is that, of course, it is n squared still, because here this loop will initially do 1 operation plus 2, and then 3 plus 4 in the worst case, and then dot 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 all the way to n, which, as we said, is all of n squared, right? Okay, so yeah, so what are we doing here, right? I think I got this wrong a little bit. I think we should go the other way. But what we're saying is, okay, here, the logic with this dynamic programming problem is, we ask ourselves, can we create a subsequence of length j? Right? Computer's lagging a little bit, but okay. Can we create a subsequence of length j? And we actually should greedy the other way, so I actually messed up here. We should start from, okay, if dp of -1 is less than num sub I, then we append, which is just what we have here, obviously. Yeah, and then we start by going here all the way to 0, right? And then break. Forgot to break. Okay, so basically this is saying, okay, what's the longest subsequence that we can make, right? So, and can we make one of, like, the longest one, can we extend that, using the current number, can we extend that to have one extra subsequence or a subsequence of length plus 1. And that's basically what we have here. If this is bigger than the biggest number, which should be at the end, then we add it to the back. Otherwise, we look for the largest subsequence that we can add this number to make it longer, using this current number as the last element of a subsequence. And here we actually replace them because in a greedy kind of way, if you have a sequence that is something like 1, 2, 3, 4, 10, and you have num sub I, and this is a length 5, say, and if you have a num sub coming up that's say 8, then you can always make a different subsequence of length 5 with a smaller number, but it's greedy because you know that in theory, if we make it smaller, then we can unlock 9 later on, where if we kept it as 10, that is not true, right? So that's basically the idea here. But you cannot go any lower, because if you go lower, you do not know for sure that you can replace it, because yeah. And with that in mind, if you print out the DP array, as we said, you can kind of see that it becomes monotonically increasing, right? So if we just run it real quick, though, maybe these aren't the perfect examples. So, but yeah, you can kind of see that they're monotonically increasing. Well, in this case, it's not really that interesting, but, and from that you can notice that you can change it to binary search. And what is this binary search? Well, you look at this and you realize that you're only looking for the first number. What are we doing here? We are looking for the first number that is actually, this, I think I messed up here. This should be equal to. That's why I'm having a little hesitancy. Because if this is equal to, then you already cannot extend it any longer, because you know this because the number before that is the same number as you have now, right? So you're not extending any subsequence. But anyway, okay. So that is less than or equal to. Oh no, that is greater than or equal to num sub I, right? And of course, once you say it this way, of course it becomes very well, I mean, it is just a binary search problem then, right? So now you have index is equal to a binary search of dp of num sub I, and then here we can just check if index is less than length of dp, then dp of index is equal to num sub I, else we want to append num sub I, right? And that's pretty much the reduction, though it is kind of hard and tricky and kind of one-off, to be honest, because this observation is kind of, I don't know. I think it's unreasonable to know, but, or like, I don't know. This is a weird way to construct dynamic programming, in my opinion, but it is good practice for harder problems maybe. But yeah, you can see really quickly that if you look at this inner loop, or inside the loop, we only do one binary search here, so it's going to be log n. Here is going to be n, so this is going to be O of n log n. And for space, is actually only, it's going to be O of n space or O of k space, where k is the output. So in that way, it's a little bit output sensitive complexity, but yeah. That's all I have for this one. Yeah. Whew. This is a tricky one, I think, to be honest. So for n log n, I mean, but definitely practice the n square dynamic programming solutions in general. happy Friday, happy rest of the week, happy weekend as that's coming up. Hit the like button, hit the subscribe button, join me on Discord. Stay good, stay healthy, stay cool, and to good mental health. I'll see you next time. Bye bye.